Okay, section 5.1, we're going to look at estimating finite sums, so finding the area underneath a curve, and we'll estimate using rectangles. So first we want to figure out, why we might want to find the area underneath a curve. So if we think about this example here, we have an object moving at a rate of 3 feet per second for 4 seconds. We want to find out how far it went, so we know distance is rate times time. So the distance traveled is 12 feet. Now, if we drew a graph of the velocity curve, it's a straight horizontal line, and if we found the area underneath that curve from time 0 to time 4, it's the area of a rectangle. 3 times 4 gives us 12. So we can see that the area underneath the velocity curve gives us that distance traveled. Well, now let's look at what happens if our velocity is not constant. We could make the connection now that the area underneath that curve gives us the distance traveled even if the velocity does not stay the same. So if we have our velocity given by v equals t plus 1, we want to find the distance traveled during the first 6 minutes. So we can draw the graph. There's v equals t plus 1. And over the course of the first 6 minutes, it's a trapezoid. Here's the general form of the area of a trapezoid. So we have a height initially of 1, final height of 7, a width of this trapezoid of 6, and we get 24. So the distance traveled, if we maintain that velocity, which increases as time goes on, we would cover 24 meters. And now we look at something like this. We have velocity, which is given by 1/8 t squared plus 1. So we have a parabola, and we don't have a formula for finding the area underneath a parabola. So if we want to figure out how far an object has gone, if it maintains this velocity, we need to figure out a way to find that area under the curve, and we're going to have to approximate. And one way we can approximate that area is by using rectangles underneath the curve. So we can use what we call LRAM, left-hand rectangular approximation. We find rectangles that meet at the left-hand corner of the rectangle. So if t equals 0, we can find the velocity, that's 1, and we construct a rectangle over that first 1 second, and then we compute the velocity when t equals 1, 9/8, we construct another rectangle, do the same thing with 2, and then with 3, and notice we don't use the final time of 4 because we're using rectangles that meet on the left-hand side. So we have the area, or we can find the area of each of these rectangles. They're all 1 unit wide, so we add up all of those areas, and we get 5.75. So the distance traveled is approximately 5.75 feet. Now, if you look at the graph here in those rectangles, clearly this approximation is an underestimate because we have all that area above the rectangles that's not being accounted for. So we could also try using the right-hand rectangular approximation method, RRAM. In this case, we make our rectangles meet on the right-hand corner. So we start by plugging in v equals 1, and then 2, and then 3, and then 4, and we can see that this gives us an over-approximation of 7.75. Another way we could go about this, which might give us a better approximation, is to use midpoint. Now, the calculations sometimes with midpoints get to be a little bit less straightforward because we need to plug in t equals 0.5, 1.5, 2.5, and 3.5. So here we'd definitely be using a calculator. And if we add up all of those, the approximate area is 6.625, which we can see is between our lower estimate and our upper estimate. Okay, so we've been using 4 subintervals. There's nothing that says we need to use 4 subintervals. We could use 8 or 16 or 1,000 subintervals. The more subintervals we make, the more little rectangles, those rectangles get narrower and our approximation becomes more accurate. So if we used 8 subintervals and we use MRAM, well, our first subinterval goes from 0 to 0.5. Halfway between there is 0.25. Then we go from 0.5 to 1, so we plug in 0.75, and so on. We end up with 8 rectangles. Now, what we should notice here that's different is keep in mind we're looking at the areas of the rectangles. This table over here gives us the velocity, but the area of those rectangles each has a width of 1/2 or 0.5. So when we add up all those velocities, we need to multiply by the width of the rectangles, 0.5, and we get our approximate area. It turns out the exact answer is 6.6 repeating, and we'll find a way eventually to come up with that answer. For now, though, the best we can do is to just come up with an approximation. Just some terminology that you might hear. Inscribed means below the curve or inside the curve. So this, if we were asked to approximate this curve here using inscribed rectangles, here's what it would look like. Circumscribed means above. To summarize, the big idea here is that the distance traveled by any object is equal to the area under the velocity curve. So if we know the velocity for some object over some period of time, we can figure out how far it went. And we will be learning how to find the exact area under the curve. That'll be coming up here in the future. For now, we use rectangular approximations, and even once we can find this exactly, rectangular approximations are still useful because there are times where we just get discrete velocity data points, right? We just know the velocity at 1 second and 2 and 3 and 4, and we don't know exactly what's happening in between. In that case, we still need to use rectangular approximations.